Good afternoon. My name is Gang Xiao, and welcome to Physics Department's 2017 Arthur Oni Williams Jr. Lecture. So far we have had more than 20 such lectures by distinguished physicists worldwide, as it will be exemplified by today's lecture to be introduced soon. Arthur Williams Jr. Was an important figure in our department. He was the descendant of two prominent Rhode Island families. You know, Roger Williams and the Onis. His forebears include Stephen Oni, Secretary of State in the cabinet of Grover Cleveland. Arthur grew up in East Providence, graduated from the East Providence High School in the 1930s, and he went to MIT on a scholarship after he won a nationwide science contest. And Arthur graduated from MIT in 1934 and came back to Brown and worked with Professor Bruce Lindsay on atomic wave function calculations for his PhD project. Afterwards, he was professor of physics at University of Maine for 3 years, and then came back to Brown and was a physics professor for 30 years. He became the chair of our department in 1955, overseeing the expansion of our physics program from acoustic physics to solid-state physics and also particle physics. And many of us here have benefited from his vision. And also from this lecture series named after him. Professor Williams was a distinguished physicist in the field of acoustics, winning the Pioneers of Underwater Acoustic Medal from the Acoustic Society of America in 1982. So now I'd like to ask Professor Sean Lin to introduce today's speaker.
Thank you, Gang. It's a great pleasure to welcome Professor John Rapey of Cornell University to Brown. Professor Rapey received his undergraduate and master degree from University of Connecticut. He went to Yale in 1961 to receive his PhD. He received his PhD from Yale in 1961. Then he stayed at Yale as an assistant professor from 62 to 66. And then he was lured away by Cornell, and he stayed at Cornell ever since. He was the John Wetherill Professor of Physics from 1987 to 2005. Professor Rapey was known for his contribution in low-temperature physics, and his work with Dave Bishop was quoted as the decisive experiment in 1978 to prove the costless thallus theory. So according to Mike, and he would have wished that John was a co-recipient of the Nobel Prize last year, but unfortunately no one can argue with the Nobel Committee, so sorry about that, John. And John was a fellow of the American Academy of Arts and Sciences and a fellow of the APS and member of the National Academy of Science. And he won Guggenheim Fellowship twice. I didn't know that you can do that, but in 1972 and 79. And he won the Fritz London Award in 2000. And let's give a round of applause to Professor Rapey.
Well, thank you for the invitation to come back to Providence. It's the hometown of my favorite author, H.P. Lovecraft. Today I'd like to talk about a series of experiments which took place a long time ago, and I'll come to that. But first, I'd like to congratulate Mike once again, after many such congratulations, on your share of the Nobel Prize. So, there is another side of Mike, or activity which he's been famous for. As I point out up here, in the 60s and 70s, if you asked who is the famous Kosterlitz, the answer would have been Hans, a really distinguished scientist, Mike's father. But during that time, Mike created a real reputation for himself as a climber. And here, so I'll show you a picture of what we call the young hard man, 1963, on a quite challenging climb, Scarpio, on Cloggy in North Wales. Well, the work I'm going to talk about was done before not everyone here was born. The ones up there in the peanut gallery, so to speak. Anyway, so I would like to go back to really the beginning of time, at least the beginning of time for liquid helium, and that's 1908, when it was first liquefied by Camerlingionis. And then there's a series of sort of landmarks along the way. But the lambda point, which is a sign of that there's a real phase transition goes on in this liquid, wasn't discovered until 1932. And you might ask yourself, why people weren't paying attention to helium? It could have been discovered much earlier. I think the reason is that shortly after the liquefaction of helium, superconductivity was discovered. And that's a so much easier subject to investigate because you have electromagnetic tools available. And helium is a neutral material, so there are problems. In 1938, however, the fact that the liquid below the transition temperature really was quite unique and had superfluid properties, something new in the world for a liquid system. It was known, of course, in superconductors, the electronic system. But so things went on. A two-fluid model was developed to describe the liquid. That was based on the ideas of Bose condensation. London was the principal exponent of this point of view. He was opposed by Landau, the distinguished Russian theorist, who made major contributions to the theory of helium, but they were in parallel, essentially, as it turned out, with the ideas of London based on Bose condensation. And one of Landau's major mistakes was to say that Bose condensation had nothing to do with superfluid helium. I don't know if he ever regretted it or ever retracted it. But anyway, then, because of the Bose condensation, there existed a background macroscopic wave function in the system, not just for a single atom, but for the whole system. And that led to the idea of quantization of flow, quantized vortices, so on, and which were experimentally realized in the late 40s by Joe Binen, and so on. And heat capacity was revisited with higher precision. It led into the glory period of critical phenomena, and helium was one of the chief substances to work on because it had real experimental advantages over other systems. And then we go on to quantized, we go to persistent currents and coherence of the condensate. Turns out the condensate is a much more robust entity than you might have imagined. And then on to two-dimensional systems, which turned out we were led into it experimentally, just as a kind of natural extension of our work. But it turns out that phase transition in 2 dimensions is really something very different than it is in 3 dimensions, which all these earlier experiments pertain to. So this is what I'm going to be talking about. The earliest indication of a phase transition actually was shown up earlier than heat capacity, and the density of the material. It increases as you cool down, as most things contract. But then there's this point where doesn't change very much. Not much was made of this at that point. But later, the heat capacity was measured in 1932, and there was the name lambda point was given to this phenomena for the obvious reason, the shape. The beautiful example of superfluid properties is the so-called fountain effect, basically an accidental discovery where there's porous media here. Helium can enter from this helium bath, fill this up to, it would normally go to there. But if you heat it, in fact, you get a jet of helium flowing out. It means that helium flows in through this porous media with essentially zero resistance. And that's where the name super comes from. It's superflow. Another such example is superflow in helium film. Now, the helium film there's nothing super about that. It's just its effect of Van der Waals attraction to the walls allows the helium to condense on the walls and build up a film. But in fact, if you have unequal levels, this film can flow in or out by a siphon effect, essentially. And this is an extremely thin layer and is essentially flowing without dissipation. So the crucial experiment really to show out what's going on is this Andronikashvili experiment, which is a torsional oscillator experiment. It's the first one of the series of torsional oscillator experiments I'll talk about. There's a fiber up here that these pile of disks hangs on, and the normal fluid acts like just that. A normal fluid is trapped between the disks and oscillates with the disks. And the moment of inertia then depends on essentially the mass of the moment of inertia of the normal fluid. And as you cool down, the normal fluid disappears, and you're left with just superfluid, which doesn't interact with the disks. And so the moment of inertia changes with temperature. And this basic technique has been how I've earned my living for quite a number of years now. This apparatus is run at low frequencies to ensure the trapping of the normal fluid between the disks. But experiments I've done are done more like a kilohertz frequency rather than 1 hertz or less. Onward. Anyway, it was established the boundaries of the phase diagram of helium as a function of pressure and temperature. At low pressures or saturated vapor pressure, you have a line separating liquid from gas here. There's a critical point out here, which also has a singularity in the heat capacity. And then you have a line here, which is a weak function of pressure. It tilts back. The slope of this line, well, if you think about hydrostatic pressure, as you go down in liquid helium, the hydrostatic pressure increases. So you essentially move up this line. And you might ask, what's the slope? Well, roughly, the transition temperature changes about 1 microkelvin per centimeter of height of liquid helium. So it means you can, if you restrict the height of the helium, you can do experiments which, it's a rather homogeneous, small range of transition temperatures. If you make, say the helium 1 millimeter thick, then you can work down to the micron level with the 10% change in transition temperature. This is important if you want to measure the heat capacity, for instance. A big sample of helium is going to have a distributed transition temperature, so what you measure will not be sharp. This problem is solved at great expense by taking the experiments to space, where they can be in free fall, in which case you lose the hydrostatic pressure and you can increase the resolution of the experiments number of orders of magnitude. And this has been done courtesy of the American taxpayer. But before that time, and with improved thermometry, Fairbank and Buckingham at Duke remeasured the heat capacity and showed it to be really sharp transition. Here's a series of resolutions. The reason they did this experiment, however, was based on an erroneous theory. There was a theory current at this time that the coherence length in the helium would be finite at the transition, and therefore the transition would be rounded at a level which they were capable of resolving. Well, there's no evidence at all here that there's any rounding at all to the transition. And an interesting way to plot this data was to plot it on a semi-log plot. So this would, if these straight lines would indicate then that the singularity is basically a logarithmic one. That was a very strong idea at the 50s when this was done, and motivated by Onsager, who had solved a different problem, namely a two-dimensional Ising problem, and showed that there was a logarithm in the singularity and an exact result. And that has a powerful effect on people's minds. And so the idea that you'd find another transition with the logarithmic singularity is extremely appealing and not critically examined, I would say, at that time. It turns out this is not logarithmic. It's slightly off from logarithm. Experiment what I was involved with is persistent current experiments. If the liquid helium can flow without resistance, then it's pretty obvious you ought to be able to create an everlasting flow around some torus, for instance. So we built this apparatus. In fact, to create the persistent currents, you would tip this donut into the horizontal position and then rotate the whole cryostat and cool it down through the transition. And that would trap an angular momentum of a flow around the torus. And then you would rotate the torus down into this horizontal position for measurement. And then perform a slow rotation about the vertical axis. Then you're making the angular momentum vector precess. And that requires a torque at right angles, which would be a torque along this axis here, which is a small fiber, and and that torque is provided by a tipping of the gyroscope slightly on that fiber. And so the degree of that tipping depends on the magnitude of the rotational speed and the magnitude of the angular momentum. Now, the angular momentum itself will depend on the superfluid flowing around this ring, and so it'll depend on the velocity of the superfluid and on the density of the superfluid. So by measuring this quantity, you can measure both critical velocities, or if you stay below the critical velocity, you can measure the density of the helium as a function of temperature. And the reason you could do that, here's a plot. Again, this is a log-log plot rather than a semi-log plot. So this is the power law. Well, the reason you could make these kind of measurements is that the magnitude of the persistent current, in fact, is a reversible function of temperature. This means that the superfluid velocity is not changing, only the superfluid density is changing. Now, this is quite contrary to what most of us would have said if you pose the question. You have angular momentum of frictionless fluid in a disk. You then change the density of the normal fluid of the system. What do you expect to happen? Well, most people would say momentum will be conserved. Well, it's not conserved. That in fact, now this comes about because the velocity of the superflow is determined by the gradient of the phase of the macroscopic wave function in the system, and that is fixed. And so it's the normal fluid, in fact, whose momentum really is changing. If you introduce normal fluid excitation to the system, there has to be some impulse. Say if you're removing some superfluid, you have to reduce the angular momentum as the superfluid is destroyed, or you introduce a normal fluid excitation. So it all works out, but there's this wonderful property that you can, the circulation around the torus is constant, and you can then measure the superfluid density. Well, on one hand, we have the heat capacity with logarithmic singularity, or almost logarithmic singularity, and then we have the superfluid density with close to 2/3. In fact, there was speculation at the time that, in fact, this might really be the rational fraction of 2/3. And this, as I say, was in the era of critical phenomena, and it was what people were doing is you write down these critical exponential forms for the superfluid density. In this case, it would be characterized by an exponent of zeta, which is modern value would be 0.675, and which is not 2/3, and it's outside experimental error of 2/3. And heat capacity is written by this sort of function, and as this function, as alpha, this exponent approaches 0, this function then becomes an approximation for a logarithm. So the logarithmic result here would be, alpha would be essentially 0. But it's not 0. It's just a small number. And these numbers are very well established these days. And they are related together, however, by scaling relations. Some of the, here's a typo here. That row should be a full-size row, but somehow I got confused with the subscript. Sorry. Anyway, there's these relations, there are a whole slew of them in the critical phenomena theory. There's various inequalities and so forth. But anyway, the important one for the relation of the superfluid was brought in by Josephson. And basically the coherence length, which measures basically the scale of the fluctuations of the system, which get larger and larger as you approach the transition, that's inversely proportional to the superfluid density. There's another relationship related to the heat capacity, which basically connects the heat capacity to the superfluid density. It comes from two-scale factor universality, so-called. A terrible name. But anyway, the amplitude of the heat capacity, this A up here, capital A, is related to inversely to the strength of the superfluid density in the transition to the cubic power. And what it means is that if you some way can reduce the superfluid density, then you're going to very much reduce the heat capacity. And in fact, in experiments I'm not going to talk about, namely done in Vicor glass, you can reduce the effective density of the helium by diluting it with this glass by a factor of 100. And here, that means that the strength of the anomaly and the heat capacity is going to go down by almost a million, become invisible in most experiments. If I had time, I could show you an experiment where we've actually resolved that. But onward. It's possible to put a helium film in one of these gyroscopes. We did that. And there's another remarkable property. If you've created a persistent current in the helium film by the usual way of rotating high speed and then stopping everything and rotating the gyroscope down and making your measurements, we find that if you sit at fixed temperature, you can add helium to the system. And again, just like changing the temperature, lowering the temperature, the angular momentum of the film gets larger if you make it thicker. And in fact, you could go on up by steps, and in fact, this is reversible. If you start pumping on the chamber which contains the film and the gyroscope, you can make the film thinner. And you can go right back down this curve, and you can go back and forth. How can that be? You know, you're adding gas from an external room temperature source. There's no momentum in that. And you're introducing it into an apparatus which is sitting still, except when you rotate it. Well, again, it's the condensate. You imagine the condensate is in fact growing as you make the film thicker, and it grows in a coherent way. I sort of liken it to epitaxial growth, where you have a crystal and you evaporate on some more of the same elements, you can get the crystal to grow. You know, and the structure of the crystal propagates as the new atoms are added. And the same thing happens with the condensate. So, these experiments are all basically done in sort of three-dimensional systems. As I say, a thin film on a 3D connected system will exhibit three-dimensional phase transition. But a natural thing to continue to would, of course, would be the two-dimensional case, and where many of the same techniques can be applied. The difference, important difference is if you have a thin helium film and you plunk into it a quantized vortex, where here we imagine a cylinder in the system, but this could just be a core of the vortex, but you get circulation around it, and there's a change in the phase of the condensate, the vicinity of the vortex. Removing this makes the system simply connected. If you plunk in this vortex, you change the topology. And hence, a vortex line introduced into the system that's basically, in the language of the present, a topological singularity, topological excitation, and hence the connection to essentially topological phase transitions, in my mind. So, this is the quick version of the, you can object if you want to say something. Anyway, in '73, Mike and David Thales published a paper in which they gave a free energy argument, basically. You might even say hand-waving argument. They came up with a prediction of a transition temperature and that vortex pairs would dissociate at transition temperature given remarkably by fundamental constants, and it would be scaled by the superfluid density per unit area. It's quite a remarkable prediction, but the important thing is, in fact, later, Mike and then later with David Nelson really made this result rigorous. First by Mike's renormalization group calculation, which was a calculation not ahead of its time, but certainly leading for its time in the application of the renormalization group technique. And it was possible to essentially get this exact result from those calculations. Now, I view this as sort of in the same order as Onsager's exact solution of the Ising problem. in statistical mechanics, there are precious few examples where, in fact, a statistical mechanical problem can be solved exactly. And this is one of the important examples. So, my connection to all of this, and is why I'm here, is an experiment which David Bishop, my student, did back in, well, the original work was done in late in 1977. I discussed those results with Phil Anderson at a Gordon conference, not Gordon conference, but Sanibel conference that winter. And I think he carried those ideas back to Bell Labs. But anyway, sometime in 79, I got a telephone call from Bell Labs from David Nelson. And David, and I believe you were there at the time, and saying, well, we have this exact result predicting a jump in the superfluid density at the transition. We know you've done these experiments. What is your number? Well, it never occurred to me that we should calculate that number because I just didn't have the imagination to believe that there would be a real exact result, coming out of an experiment. But so I went down to the lab and approached David and said, David, I've got this call from Bell Labs. They want to know what the size of the jump is in our signal. But I didn't tell him what the answer was, or might be. So he calculated this, and lo and behold, it came out within 10% of the value you calculate if you put in these constants. Well, the experiment he had done is a torsional oscillator experiment. The geometry was created by taking a long strip of mylar film, certainly reached from here to the end of this room, and wrapping it on a little spool, sprinkling it with very small particles to keep the pieces of mylar apart, and then encapsulating it in a chamber with the cover and sealing, making superfluid tight, mounting it on a torsion rod. And I think if I've moved that slide out of there. Okay. Anyway, so when all this was together, it would be assembled like this. There was a little electrode on the top, which we would use a capacitor to push and pull on the oscillator to set it into oscillation, and then one on the opposite side of this little electrode to detect the motion. So you could see very, very small angular oscillations of the system. Now the period of oscillation, just as in Andronikashvili's experiment, depends on the torsion constant K and also on the moment of inertia of the cell that's oscillating. The helium in here makes up part of that moment of inertia. So if the helium coupling to the substrate changes with temperature, you get a change in the period of the oscillation. The secret of this method is that, in fact, this period, because these are high Q oscillators operating at low temperatures, the period could be stable to at least a part in 10 to the 8th, and in some experiments we've gone to part in 10 to the 10th. So it allows you to see exceedingly small changes in the moment of inertia. And so, in fact, there's no problem with signal size in these experiments. Well, what do you see? If we measure the period of the oscillator, say at fixed temperature, here we're at 0.3 of a degree, and you add helium to it, you see that increases the moment of inertia of the mylar inside the cell and the torsional oscillator. So the period increases. The helium is completely coupled to the substrate at this point, but at this temperature and at this film thickness, essentially, boom, the period drops very abruptly. And then, as you continue to add helium, it increases. Now, our interpretation of the fact that it's not just flat here is that the Mylar geometry is not perfectly cylindrical. Given, it's not because of the spiral nature of the structure, but in fact it can be slightly egg-shaped. And as soon as you depart from the cylindrical geometry, then the superfluid fraction gets pushed to some degree by the oscillation, and it will contribute to the moment of inertia. Another possibility is that there is some kind of drag force involved in the system. But although this measurement, let's say, at constant temperature is rather interesting, much more interesting data can be obtained by working at finite fixed film thickness and varying the temperature. Then the period of the oscillator is plotted here for films of different thicknesses. These data have been plotted, constants have been added to make them look beautiful and agree. They don't actually agree. This curve would lie down here. The next one would be a little bit higher because of the additional helium and so on. So they've been corrected, but what's really important is the difference between this trend line and the actual data. So you can take this difference and plot that against temperature. And, well, this is another aspect. Let me go on. This is what you get from plotting, taking that difference. Here's the change in period versus the temperature for a series of films. And you see they're rather flat, and then they drop precipitously. This is entirely different than what you see in the 3D system. 3D, the superfluid density comes over and comes down with the 2/3 power law to the transition. Another striking and a very important aspect here, in fact, is the fact if you look at the dissipation in the system, you find that the sharp drop in the superfluid behavior is, like for instance here, is correlated with a strong dissipated peak in the system. This again is completely different than what one sees in 3D. Another difference, for which I don't have a graph, is that if you measure the heat capacity going through one of these, quotes, transitions, you essentially see nothing in the 2D system, unlike the lambda point, which dominates the 3D transition. So it's very clear that the transition in a 2D helium film is a very different animal than what you see in 3D. And here's another one. Okay. So here's an example showing the plot of the change in the superfluid response and then the dissipated peak. Well, we knew, of course, and certainly in the discussion I had with Anderson, was that vortices had something to do with this phenomenon. I mean, basically, this is the graph I showed him in Sanibel in early 78, I guess, 79. But this important thing is this is a dynamic experiment. It is not the experiment, the situation considered by Koslowitz and Thowas, or Koslowitz and Nelson. They were doing static theory. And so, although this kind of result is sort of what you might expect, and in fact, the size of this, if you draw a line down through the size of this jump here is more or less what you would expect from the Kosterlitz-Thomas static theory. Though still, as experimentalists, one is a little unhappy, because we're to say that a dynamic observation is the same as a static one is a big jump. So what we needed was an extension of the static theory to the dynamic case. And now this was provided by a long string of names, Abagankar, Halpern, Nelson, and Sidgett. It sort of started with experimental discussions I'd had with Vinay Abagankar and Eric Sidgett, because they were both at Cornell. And so I just went up to the 5th floor where they were and told them we have these results. And Eric liked to say he described this as the finger. And so they got to work on trying to extend the static theory to the dynamic case. And they, in fact, published a paper. Once we had the theory, then we could actually try and fit the data. And here, the solid curves that you see here are fits of the dynamic theory to what we observed in the experiment. And one of the important parameters, in fact, is the dot, very small, well, in the back of this hall, I'm sure you can't see this, but there's a very small dotted line which terminates at this point. That is the prediction of the static theory. So in static theory, say you drop to 0. But in fact, in the dynamic case, the transition as temperature is pushed up a bit, but using this is the number which is used as the parameter in this fit. So the other thing is a diffusion constant, basically, related to how fast the vortices can move apart. Now, what's the picture? Well, the picture is that below the transition, you have pairs of vortices which are essentially bound together. When you oscillate the system, you have a superflow past them, and they kind of move apart a little bit, and they rotate, but they still basically stuck together. As you go up in temperature, their binding is reduced, and so they move more. But suddenly, at a certain point, the system just becomes unstable, and boom, you get very rapid change in the superfluid response. And because you're dealing with these systems that are moving around, they get out of phase with the motion of the oscillator, and you then naturally get dissipation. And so the fact the existence of the dissipation peak is a very important element in supporting the argument this really is going on with the dissociating vortex system. If you take the jump in the superfluid density at the transition, namely this drop from here to here for a whole series of experiments. In our case, we're doing a dynamic, well, all the experiments have been dynamic, but we're the only ones who have actually measured the dissipation as well. So you could get this more rigorous fit. But there have been many other measurements of behavior of superfluid films in 2D, and you can go back to them and basically extract, say, what was the jump when their signal disappeared, for instance. They couldn't see it anymore. And so I went back and I looked at the early experiments of Rudnick, Michel, Halleck, and there should be some data on here from Yang's experiment. But anyway, these are the third sound ones. Okay, so here's a collection of all these measurements we pulled off these other experiments. And here's a line through it, which is basically the slope, which should bring in agreement with the Kosterlitz-Thomas theory. So it's you know, the data is scattered, and there's sort of a kind of 10% uncertainty in this slope, but it's pretty damn good agreement, considering that here's a real physical experiment, and here's this esoteric theory. So that's basically the justification for me being here today. It's a measurement. Okay. So that graph has appeared in our paper, but there's an earlier version which is hand plotted. And in fact, I can recognize my own handwriting here. I don't know whether I plotted some of this. Dave Bishop, I think, plotted other parts of it. But anyway, this graph has made its way by a rather circuitous route to the Nobel Museum. It was actually donated by David Thawlas. It says down here, you can't read it, I'm sure. And it was donated by David Thawlas, of course, I guess didn't really know where it had come from. It had been hanging in his office for a long time, probably for 20 years or something. Although actually, Dave Bishop told me that he gave this picture to David on the occasion of your Onsager Prize. So that would date it. I don't remember when that was. But what? 2000, okay. So it had maybe 15 years in David's office. So he donated to the museum, and that's where it is today. So, well, thank you very much. Because of my hearing problems, I have an interpreter here if anyone wants to ask a question.
Okay, so because this talk is being videotaped, so any question should be addressed to the that microphone, and now I will give you the microphone as well. Okay, so now the talk is open for question.
For lucky, there'll be no question.
Okay, well, let me ask you for, to break the ice. Okay, I noticed in the Q factor measurement for films with different thicknesses, I noticed for the thinner ones, the peak got sharper. This is very different from superconducting films, where you would expect, well, we do see broadening rather than narrowing. Yes.
Okay. Yeah, and in fact, this is not a complete display. We have going even further up. And it is a very interesting phenomena which we don't really understand, but in fact, basically at half-layer intervals, the transition become quite sharp. And for instance, this one here, which is almost zero thickness, is very sharp, relatively speaking. And then back up at 1 degree, we again have a very sharp transition. And the best fits that we were getting using the dynamic theory were always to the sharp ones. You can fudge those fits by saying, well, maybe there's some frictional element on the vortex motion and to broaden the transition. So I suspect that there are pinning effects present, just due to defects in the substrate, which for some reason disappear effectively at certain magical coverages. But we certainly don't understand that in detail.
Okay, so that sharp peak is just an anomaly. It's not really a systematic effect.
Well, I don't know whether it's the anomaly or it's the regular. Okay. The broad ones may be the anomaly. No, but. No.
So how do you control the thin film thickness? Is it the gap of the Mylar sheets?
How do we measure it?
Yeah, how do you control that? Yeah.
Oh, the way we measure it is by having a capacitor. And so the thickness of the film absorbed in the capacitor changes the capacitance. And then now there may be a, the van der Waals attraction in the capacitors may be different than the Mylar. So, but these are rather thick films, and but that's how we get a parameter, and everything, as you saw when the angular momentum was building up and so on, it's very linear. And so we think that there may be a factor, the film may be 10% thicker, but I think it's a constant factor. Otherwise, you probably would see curvature of some sort in that data. Okay. And the important thing there is, of course, we're doing it at a very low temperature where other kinds of excitations of the system are pretty negligible. So, third sound excitations, riplons, for instance, would depend on the thickness of the film, but they're not contributing anything very observable. Okay.
Any questions from the students? Can I ask one more?
Sure.
So the helium has had several Nobel Prizes. Is there another one?
Sorry?
Helium has had several Nobel Prizes. Is there another one?
Well, in 2004, there was great talk about another Nobel Prize in helium, namely for the supersolid.
Okay.
Well, we know where that's gone. It's hard to say. I don't know. It has been very rich, particularly if you include helium-3, because there have been 2 Nobel Prizes in helium-3 and then helium-4. How many? 4 or 5, 4 or something. I haven't counted. Too many to count. But it has been a very productive area in those terms. But it's also, a wonderful area to just illustrate fundamental physics.
Oh, hi, Professor Rapi. So I'm a student here, and my question is kind of naive. So have you ever considered a 2D supersolid?
Should I give students for advice?
2D supersolid. Is that your question?
Yeah.
Do you think, is it possible to have 2D supersolid?
For there to be a supersolid?
Well,
Well, I should have retired. I retired formally in 2004. I got sucked into this supersolid business. I had promised my wife I would retire. She's held it against me that Anyway, it's been a lot of fun, but it's turned out not to be what we thought it was, or thought it might be in the early days, namely a real supersolid phenomenon. It turns out it's a complex mechanical problem. And as I've been saying to people, if we'd been mechanical engineers, we probably would have solved this or realized what was going on maybe 5 years earlier, because we would have done a careful mechanical analysis of our apparatus.
so maybe I will follow his question. So what happened to two-dimensional solid helium? Is it possible?
Well, I don't know if it's possible. There is the reentrant phase that's been observed, in fact, discovered by Paul Kroll on graphite. Whereas when you're filling the second layer in graphite, there appears to be a superfluid phase, which increases in magnitude as you increase the coverage. This is all on the second layer. I mean, most of you probably know that helium forms very well-defined layers as you add helium on top of it. Anyway, in the second layer, you get this superfluid response, which doesn't look like a Kosterlitz-Thouless behavior. And some people have speculated that that, in fact, is this 2D supersolid. My mind is open on that. I'm not quite open. I think probably the answer is no. But, but that's not based on any deep understanding of what's going on there. But so it is a possibility. But interestingly enough, as you complete the second layer, this superfluid behavior disappears. And then when you start to fill the third layer, then you get something which looks Kosterlitz-Thouless like, sharp drop and so on.
Any more questions? Oh, one more.
Hi, Professor. So I think it's very rare that, well, being a student in high energy experiment, I think it's very rare that in a modern scientific field you get to look at phenomena that have very clear and direct applications. And I would like to know what you're most looking forward to as an application of thin films possible. Doesn't even have to be in existence today.
Okay, Professor Rapey has a little hearing problem, so I'm going
Yes,
to
bad.
translate.
Big
Okay.
hearing problem.
Okay, so the student is a high energy experimentalist, and
Yes.
then he works on things that are not practical. Sorry, okay. And then your work is obviously more related to the real world, and then he was asking you any applications of the superfluid films. Is that correct? Okay.
The only application I know of, which has not panned out, was to use electrons decorated on helium films as a unit in a quantum computer. And their positions would be controlled by a substrate below the film and so on. But no is the answer, basically. It's wonderful to have your work supported, you know, for something which isn't going to be of great practical importance. But, you know, superconductivity was discovered in 2009 or something, right out, or maybe even earlier. But anyway, it took many, many years before the MRI machine appeared on the scene, or the magnets that could run the super collider at CERN. And so it's sometimes the lifetime of a single individual before some practical application comes out of something. And so to ask at the moment, what use is this? It's almost a useless question. He said.
I claim myself a younger generation of experimental physicists in condensed matter. My personal research experience was that in the 80s, I was motivated in studying some of the following up of a system like xenon graphite, the 2D phase transitions in that system. That system helped develop the development of X-ray and the neutrons techniques, and later on the surface science on the development of scanning tunneling microscope. So in fact, what you find is the experimental condensed matter physicists ended up not in academia, but in industry, helping develop all this electronics, the technology in computer industry. So to my dismay, that most of my students ended up in industry. Only one left as a professor. So I feel complete failure as a professor.
Well, I think this work is extremely valuable for students as training. 'Cause, I mean, and what typically most of my students don't work on liquid helium. I mean, one exception, say, is Moses Chan, but the others are David Bishop, he's Dean of Engineering at BU. There's Dave McQueenie, who's the Vice President at IBM for software development. There's Gain Wong, who has his own Genome Institute in Alberta. And, you know, why? I mean, these people who develop, you know, it's a research area where you can actually do something different on a short time scale, and it gives opportunity for your imagination to really take hold. And so I think that's why these students have been flexible when they move out, you know.
Right. Well, I apologize for saying that the hydrogen experiment is not useful, but I think you still learn this important skills as much as you do in condensed matter experiment. In fact, yeah.
Okay.
Okay, so if there are no more questions, let's thank Professor Rapey again.
Thank you.